Welcome to that of the UG students for the JAM question solution 2022 and the organic chemistry, and this is related to that of the NEET and JEE guidelines. Now we are going to that of the second slide, that is the related to the enolate derivatives of different substrate. In case of the lithium enolate, it can add at faster rate compared to that of the silyl enolate and zinc enolate. The silyl enolate is very much stable, as we know that any type of the enolate can be stabilized by the using that of the trimethyl silyl chloride, and it is stable at the room temperature. So since it is more stable, so its reactivity is slower. Hence the silyl bond can be Si bond can be cleaved in presence of the fluoride minus. So it has slower rate for the addition with that of the aldehydes. But we know that the lithium enolate has greater reactivity, as the O minus and Li plus is tight ion pair formation, and it easily react with that of the aldehydes. And in case of the zinc enolate, the rate reactivity is medium, because the zinc has the stable configuration, that is the D10 configuration, and the enolate can added to that of the aldehyde via the cyclic tension state. This is the chair-like tension state. We get that of the aldol type product. So the stability of the enolate is that is in the order in the stability, means the 2 is greater stable compared to that of the 3 compared to that of the 1. So the rate of the addition to that of the aldehyde is 1 greater than 3 greater than 2. Next, if we go to that of the KCP versus TCP enolate, if we treated with that of the cyclohexane derivatives of the unsymmetrical substitution, in case of the phenyl substitution, or in case of that of the in case of LDA, the two type of enolate is formed. One is that this is the KCP enolate, and this is the TCP enolate. TCP enolate is the more substituted enolate, and KCP enolate is the less substituted enolate. At low temperature, in presence of the lithium diisopropyl amine, this is the structure of lithium diisopropyl amine. It always enolate formation to that of the less hindered phase, and we get that of the less hindered substituted enolate, that is the KCP enolate. Here the TCP enolate is not formed, but in presence of that of the trimethyl silyl chloride, the trimethyl silyl chloride has greater stability with that of the enolate, and it is stable at the room temperature, and we get that of the TCP enolate at higher amount compared to that of the KCP enolate. Hence, in presence of the cyclohexanol known in presence of the trimethyl silyl chloride in triethylamine DMF and D plus condition, we get that of the enolate, a stable enolate, and then this stable enolate can be cleaved by presence of the titanium tetrachloride with that of the electrophilic reagent. We get that of the 62% yield of the alkyl substituted cyclopentanone derivatives. And this is the interesting point for that of the KCP enolate versus TCP enolate. In presence of the only ordinary base or less hindered base, we always get that of the KCP enolate, but in presence of that of the triethylamine at high temperature, or in presence of the less hindered base, we get that of the more substituted enolate with higher yield. Next, we go to the practical questions. We know that the Brady's reagent means 2,4-dinitrophenyl hydrazine. Thus, this Brady's reagent can easily be prepared by the reaction with the 2,4-dinitrofluorobenzene in presence of the hydrazine via the nucleophilic substitution reactions. Here, the negative charge can be stabilized by the minus R effect of the 2 electron withdrawing group, and by the elimination of the F minus ions, we get that of the 2,4-dinitrophenyl hydrazine derivatives, and 2,4-dinitrophenyl hydrazine derivatives has greater reactivity to that of the aldehyde, and we get the yellow precipitation with that of the aldehyde. Hence, the given problem is that the reaction of 2,4-dinitrofluorobenzene with hydrazine produces a yellow to orange solid X, means this is the X, and used for the identification of functional group G. G means the aldehyde, and X and G means the 2,4-dinitrophenyl hydrazine is the X and aldehyde is the G. Now, this 2,4-dinitrophenyl fluorobenzene has also been used for the preparation for the identification of the N-terminus derivatives of the amino acids, and this is known as the Sanger methods. and this Sanger methods has been used for the nucleophilic substitution with the 2,4-dinitroplurovenzene with the peptides, and after hydrolysis we get the N-terminal derivatives, where the N-terminal derivative can easily be identified from that of the Sanger method using 2,4-dinitroplurovenzene. And the drawbacks for the Sanger method is that only the N-terminal amino acid can be determined, but the sequence of the amino acid cannot be determined using the Sanger method. For that reasons, Edman degradation had been used for the N-terminus determinations, and we get that of the phenyl thiouridentine derivatives, and these phenyl thiouridentine derivatives is not is stable, and we can easily get that of the sequence of that is the sequence of the amino acids can be determined using that of the Edman degradation, and these two reactions is very important in the peptide chemistry. Now we go to the thermodynamic equilibrium. What is the thermodynamic equilibrium? We know that the ester can easily be interexchanged, that is the trans-esterification reactions can also be occurs using that of the different alkyl with that of the esters. Here the alcohol can attack to that of the carbonyl, produces a tetrahedral intermediate, and then this tetrahedral intermediate undergoes cleavage of the CO bond, produce the phenoxides ions, and these phenoxides ion can be stabilized by the resonance effect. So the forward reaction can also occur. In the second case, the amide bond, we know that the amide bond is more stronger than that of the ester bond. So here the amide nitrogen lone pair is attacked to that of the carbonyl and produces a tetrahedral intermediate, and this tetrahedral intermediate cleave down to give the alcohol and the amide derivatives. But in the third case, we know that the acid chloride is very much reactive. For that reaction with that of the acid chloride with the amines, the reaction always go to that of the backward direction, and the amide group is formed, that is the left hand side, the right hand side equilibration is not occurs. Or in the last cases, but here the water molecule cannot cleave the amide bond, as the amide bond is very stronger, so the water molecule cannot cleave to give the carboxylic acids and the amines. So the given problem, the equilibrium shifted to that of the right hand side in case of that of the A and B. Now if we go to that of the thermodynamic equilibrium, here the different type of the acid chloride react with that of the alkoxides to get that of the esters in by the cleavage of the Cl minus. From this equilibrium we can say that the starting material is converted to the product. The product is more stable compared to that of the starting material. Again, the ester group can also be hydrolyzed to give that of the final product with the forward equilibration. Now we go to that of the pericyclic reaction. We know that in case of the cycloaddition reaction, diene and the dienophile undergoes addition in presence of the heat to get that of the different type of the cyclic derivatives. But here the condition for the Diels-Alder reaction is that the two ene group must be present in the S-cis conformation. Here the S-cis conformation present in case of the anthracene derivatives and in case of the furan derivatives. But here the double bond is locked in the trans conformations, so the Diels-Alder reaction here did not take place. But in case of the pyrrole, the simple conjugated addition and the aromatization, we get that of the substitution product instead of that of the Diels-Alder reaction. So the given problem, the answer is that anthracene derivatives and the furan derivative participate in the Diels-Alder reaction. And this is the related problem, that is the stereoselectivity of the cycloaddition reactions. In case of the diene, the stereoselectivity is retained after the addition. Here in case the phenyl group present in the outer side, so it go to that of the below side, and the phenyl orientation is same. So the phenyl after addition, the phenyl group orientation becomes same. Here the alkyl group orientation is different. One is the inside, another is the outside. So after the addition, the inside group go to that of the above sides and the outside group go to that of the below side, and we get the stereochemistry is written. Similarly, if we see that of the exo and endo addition, this green hydrogen atom is in the right sides, so it must go to that of the one direction, and this methyl group and the aldehyde group in the opposite side, or means these two groups in the same side. So the hydrogen group after addition should be in the same side. This is the hydrogen group in the green sides, that is the same sides, and this ketone and methyl group is in the below sides. And similarly, if we take the hydrogen atom, this hydrogen atom and this hydrogen atom, these two hydrogen atom in the opposite orientation, one is the lower side, another is the upper side. So after the addition, we get the stoichiochemistry junction in the cis orientation. But in case of the ketone system, by the endo orientation, we get that of the cis orientation. Here the both type conformation is attained, and hence the hydrogen group is in the same sides, and we get that of the cis product. These are the upcoming video coming in the next weeks. Thank you for seeing my video.